Hello again, and welcome to our latest chapter of Forensic Science. We're looking at Chapter 12, Drugs of Criminalistics, an Introduction to Forensic Science. As always, it's a pleasure to have you all. Likes and subscriptions and subscribes are not necessary, but they are fun to see. Getting into drugs, a drug can be defined as a natural or synthetic substance that is used to produce a physiological or psychological effect in humans or other higher order animals. The nature of a drug experience can be approached from two distinctly different aspects of human behavior: psychological dependence and physical dependence. Psychological dependence, the common denominator that characterizes all types of repeated drug use, is the creation of psychological dependence for continued use of that drug. Emotional factors that play a part in drug dependence: the user's personal characteristics of the user, his or her expectations about the drug experience, society's attitudes and possible responsibilities, the settings in which the drug is used. The intensity of the psychological experience with a drug is difficult to define. Some drugs, like alcohol, heroin, and cocaine, with continued use, lead to a high degree of involvement. Others, such as marijuana and codeine, have a lower potential for abuse. Our general knowledge of alcohol consumption should warn us of the dangerous and generalizing when it comes to drug abuse. Physical dependence is the physiological need for a drug that has been brought about by its regular use. The desire to avoid withdrawal sickness or abstinence syndrome ultimately causes physical dependence or addiction. Marijuana, LSD, lysergenic acid diethylamide, and cocaine are common drugs of abuse whose regular use does not lead to physical dependence. Common classification of drug abuse are narcotics, depressants, stimulants, and hallucinogens. Narcotic drugs are analgesics, meaning they relieve pain by a depressing action on the central nervous system. Their depressant effects impact blood pressure, pulse rate, and breathing rate. The regular use of a narcotic drug will invariably lead to physical dependence. The most common source of narcotics is opium, extracted from poppies, the sap of poppies. Morphine is readily extracted from opium and is used to synthesize heroin. Addicts frequently dissolve heroin in water by heating it in a spoon and then inject it in the skin. Heroin produces a high that is accompanied by drowsiness and a sense of well-being that generally lasts for 3 to 4 hours. Codeine is also present in opium, but it is usually prepared synthetically from morphine. OxyContin, the active ingredient in oxycodone, is not derived from opium or morphine, but has the same physiological effects on the body as opium narcotics. OxyContin is prescribed to several million patients per year for treatment for chronic pain. Personally, I had it for my wisdom teeth that got removed, though I suggest you only use it sparingly. It can actually become very addictive if you're not careful. Methadone is another well-known synthetic opiate. Methadone, which is pharmacologically related to heroin, appears to eliminate the addict's desire for heroin while producing minimal side effects. Thank goodness. Hallucinogens are another class of drugs Marijuana is the most widely used illicit drug. Hallucinogens, hallucinogens cause marked changes in normal thought processes, perceptions, and moods. Marijuana is the most controversial drug in this class because its long term effects on health are still largely unknown. Marijuana refers to a preparation derived from the plant cannabis, or the series of chemicals from that plant, cannabinoids. The chemical substance largely responsible for the hallucinogenic properties of marijuana is known as tetrahydrocannabinol, or THC. Tetrahydrocannabinol content of cannabis varies in different parts of the plant, generally decreasing in the following sequence: mostly in the resin, somewhat less in the flowers, even less in the leaves, little THC in the stem, roots, or seeds. THC-rich resin from the cannabis plant is known as hashish. Marijuana does not cause physical dependency, but the risk of harm is in heavy, long-term, disorganized use. Other hallucinogens include LSD, mescaline, PCP, polycyclidine, psilocybin, and MDMA, also known as ecstasy. Lysogenic acid diethylamide, or LSD, is synthesized from lysergic acid and can cause hallucinations that can last up to half a day. Phencyclidine, or PCP, is often synthesized in clandestine laboratories and is often smoked, ingested, or sniffed. Phenylcyclidine, PCP, is often mixed with other drugs such as LSD and amphetamine, and is sold as a powder called angel dust in capsule or tablet form. Oral intake of phencyclidine first leads to feelings of strength and invulnerability, which may turn into depression, tendencies toward violence, and suicide. So, not worth it. There are also depressants, which are substances used to depress the functions of the central nervous system. Depressants calm irritability and anxiety and may induce sleep. These include alcohol, which the ingredient of alcohol is ethanol, barbiturates, anti-anxiety drugs, and for a variety of substances that can be sniffed, such as airplane glue. Yo, really? Airplane glue, model cements, or aerosol gas propellants, such as Freon. Yo, some people are just desperate. Depressants like alcohol, another name for it is ethyl alcohol, enters the body's bloodstream and quickly travels to the brain, where it acts to suppress the brain's control of thought processes and muscle coordination. Barbiturates, or downers, are normally taken orally and create a feeling of well being, relax the body, and produce sleep. Anti anxiety drugs, unlike barbiturates, produce a relaxing tranquility without impairment of higher thinking faculties or inducing sleep. Two examples being Valium or Xanax. Huffing or sniffing materials containing volatile solvents has immediate effects such as exhilaration, but impairs judgment and may cause liver damage, heart damage, and brain damage, and unsurprisingly, death. Stimulants. This is the drug classification which includes amphetamines, sometimes known as uppers or speed, and cocaine, which in its free base, that's a chemical term, in its free base chemical structure, it is known as crack. Cocaine and crack, they are the same thing, just whether or not there is an extra acidic proton or not. Stimulants are substances taken to increase alertness or activity, followed by a decrease in fatigue and A loss of appetite. Stimulants like amphetamine or methamphetamine, often injected intravenously, cause an initial rush followed by an intense feeling of pleasure. This is followed by a period of exhaustion and a prolonged period of severe depression. Yo, that's so not good. Cocaine extracted from the leaves of Erythoxylon coca causes increased alertness and vigor, accompanied by the suppression of hunger, fatigue, and boredom. Crack is cocaine mixed with baking soda and water, then heated. Crack is often smoked in glass pipes, and like cocaine, stimulates the brain's pleasure center. Club drugs refer to synthetic drugs that are used at nightclubs, bars, and raves, like MDMA, GHB, rifipronol or rihipnol, roofies, ketamine, and methamphetamine. GHB and rihipnol are depressants that are often connected to drug facilitated sexual assault and rape. Anabolic steroids are synthetic compounds that are chemically related to the male sex hormone testosterone. Testosterone is really in both males and females, but it's the predominant sex hormone in males, whereas estrogen and progesterone are predominantly higher concentration in females. Testosterone promotes the development of secondary male characteristics and accelerates muscle growth. Steroid abuse first received public attention when athletes were discovered using these substances to enhance their performance. And it really is just ugly. Drug control laws. The U.S. federal law, known as the Controlled Substances Act, CSA, serves to illustrate a legal drugs classification system created to prevent and control drug abuse. The federal law establishes 5 schedules of classifications for controlled dangerous substances on the basis of a drug's potential for abuse, potential for physical and psychological dependence, and medical value. Schedules of classification. Schedule 1 drugs have a high potential for abuse and have no currently accepted medical use, such as heroin, marijuana, methaqualone, or lysergic acid diethylamide, LSD. At least on the federal level, no, no accepted medical use. Schedule 2 drugs have a high potential for abuse and have medical use with severe restrictions, such as cocaine, phencyclidine, PCP, and most amphetamine and barbiturate prescriptions. Schedule 3 drugs have less potential for abuse and a currently accepted medical use, such as all barbiturate prescriptions not covered under Schedule 2, like codeine and anabolic steroids. Schedule 4 drugs have a low potential of abuse and have current medical use, such as Davron or Darvon, phenobarbital, and some tranquilizers such as diazepam, known and chlordiazepoxide, known as Librium. Schedule 5 drugs show low abuse potential and have medical use, such as opiate drug mixtures that contain non-narcotic medical ingredients. Collection and preservation. The field investigator is responsible for ensuring that the evidence is properly packaged and labeled for laboratory. Generally, common sense is the best guide, keeping in mind that the package must prevent the loss of contents and or cross-contamination. Often the original container in which the drug was seized will suffice. All packages must be marked with information that is sufficient to ensure identification by the officer in the future and establish the chain of custody. Drug identification. The challenge or difficulty of forensic drug identification is to select analytic procedures that will ensure the specific identification of a drug. The scheme of analysis is divided into two phases. Screening tests are nonspecific and preliminary in nature to reduce the possibilities to a manageable number. Confirmation tests are a single test that specifically identifies a substance. Qualitative versus quantitative. Another consideration for selecting an analytical technique is the need for either a qualitative or a quantitative determination. Qualitative determination, determining the identity of the material. Quantitative determination, determining the percent composition or amount of the components of a mixture. So qualitative, more colors, whatnot, name, and identity, and quantitative, more concentration, numerical value analyses. Preliminary analysis. Since an unknown substance may be any one of 1,000 or more commonly encountered drugs, the analysis must employ screening tests to reduce these possibilities to a small and manageable number. Screening is often done by subjecting the material to a series of color tests that will produce characteristic colors for the more commonly encountered illicit drugs. The Marquis test will show up for heroin and amphetamines. The Dili-Copania is for barbiturates. Duquesnoy-Levine will help indicate if there's marijuana in a sample. Van Erck for LSD, and the Scott test for cocaine. Microcrystalline tests can also be used to identify specific drug substances by studying the size and shape of crystals formed when the drug is mixed with specific reagents. Confirmational determination. Once the preliminary analysis is completed, a confirmational determination is pursued. Forensic chemists will employ a specific test to identify a drug substance to the exclusion of all other known chemical substances. Typically, infrared spectrophotometry or gas chromatography, mass spectrometry is used to specifically identify a drug substance. Chromatography is a means of separating and tentatively identifying the components of a mixture. The theory of chromatography is based on the observation that chemical substances have a tendency to partially escape into the surrounding environment when dissolved in a liquid or when absorbed on a solid surface. Henry's law. When a volatile chemical is dissolved in a liquid phase and is brought to equilibrium with an air phase above it, there is a fixed ratio between the concentration of the volatile compound currently in the air and its concentration in the liquid, and this ratio remains constant for a given temperature. Chromatography. One phase is always made to move in one direction over a stationary or fixed phase. Those materials have a preference for the moving phase, will slowly pull ahead and separate from those substances which prefer to remain in a stationary phase. In the chromatographic process, the molecules present in the blue balls have a greater affinity for, for the upper phase and hence will be pushed along at a faster rate by moving air. Eventually, the two sets of molecules will separate from each other, completing the chromatographic process. So, taking components in a liquid and gas phase, slowly separating them so that components of one type are separated from components of a different type of identity. Gas chromatography, also called GC in chemistry, the moving phase is actually a gas called the carrier gas, which flows through a column. The stationary phase is a thin film of liquid contained within the column along the surface. After a mixture has traversed the length of the column, it will emerge separated into its components. The written record of this separation is called a chromatogram. The time required for a component to emerge from a GC column is known as its retention time, how long it was retained in the column before it finally reached the detector. And here's just an example of a basic gas chromatography instrument. Usually chemists do not call these machines, they call them instruments. Just in case you ever have to talk to a chemist for um, professional testimony or whatever. And usually your sample is injected into a port, which is at a very high temperature, and a carrier gas helps traverse that sample through a column, and with time it breaks up into different components that reach the detector at different times, and we'll get different readings for each different components along that chromatogram. The actual visible part, or the output data from a gas chromatographic analysis. An unknown mixture of barbiturates is identified by comparing its retention times in the top column to a known mixture of barbiturates. So essentially, taking a closer look at this, what we're seeing is that sacubitril and pyridinol show up around 3.5 and 4.5 minutes, whereas a mixture that might have a few other things, this is the reference sample. Therefore, we know that we have our two known samples here. So the top is the unknown mixture, and then our known sample, where we know each component that comes off. We can compare them and see the identity of which is which. Thin layer chromatography, or TLC, uses a solid stationary phase that does not move, usually silica or alumina, usually coated onto a glass plate, and a mobile liquid phase that travels through the tube or up the plate and is used to carry the sample up the plate or down the tube, whichever is used. And as the liquid phase is carrying the sample, different components will travel at different rates through the stationary phase. The liquid will slowly rise up the plate in thin layer chromatography by capillary action, causing the sample to become distributed between the stationary phase and the moving liquid phase. When I talked about moving down a tube, I was actually talking about LC, or liquid chromatography. Because most compounds are colorless, the materials must be visualized uh, by placing the plates, once the components have been separated, under ultraviolet light and spraying the plate with a chemical reagents. The distance a spot travels up a thin layer plate can be assigned a numerical value known as an RF value. Here's an example of, in the bottom left, a thin layer chromatography. A liquid sample is spotted onto a granular surface of a gel-coated plate, and then on the right, the plate is placed onto a closed chamber that contains a liquid. As the liquid rises up the plate, the components of the sample distribute themselves between the coating and the moving liquid. The liquid is separated, or the mixture is separated. In an ideal world, the mixture separates with substances with a greater affinity for the material for the moving liquid traveling up the plate at a faster speed, whereas things that have less of affinity for the moving liquid or more affinity for the solid phase will be held back from traveling further up the plate. The rinsing solvent's original spot that was toward the bottom of the plate has now had time to separate into different components or separate several different spots. Spectrophotometry. Just as a substance can absorb visible light to produce color, many of the visible radiations of the electromagnetic spectrum are likewise absorbed. Spectrophotometry measures the quantity of radiation that a particular material absorbs as a function of wavelength and frequency. The spectrophotometer is the instrument used to measure and record the absorption spectrum of a chemical substance. The components of a spectrophotometer are a radiation source, a monochromator or frequency selector, a sample holder, a detector to convert electromagnetic radiation into an electrical signal, a recorder to produce a record of the signal. The absorption spectra can be done in the visible light region, ultraviolet light region, or, depending on the instrument, even the infrared region. So visible light, UV light, which is higher energy, higher frequency than visible light, or infrared, which is lower energy, lower frequency, longer wavelength light than visible light. Here's the basic parts of a simple spectrophotometer. There are many kits that actually make home versions for simple use. There's some source of electromagnetic radiation, aka light, either visible light, UV light, RI light, or IR light. Prism, once the light goes through a prism, it disperses the radiation into component wavelengths, and a slit is used to select for specific wavelengths of light, which that specific wavelength then travels through a sample cell containing our material. And then whatever light is absorbed in the sample, whatever light is not absorbed is able to pass through the detector. Therefore, we're able to tell that the amount of light that we initially had versus the amount of light that reached the detector, the difference would be the amount that got absorbed by the actual sample cell material, and that is recorded on the recorder. And here we get an absorption spectrum of a chemical substance that allows us to identify the particular substance or range or substances inside that vial. UV and IR spectrophotometry, or ultraviolet light and infrared light. Currently, most forensic laboratories use UV and IR spectrophotometers to characterize chemical compounds. The simplicity of the UV spectrum facilitates its use as a tool for determining a material's probable identity, although it may not provide a definitive results. The IR spectrum produces a far more complex pattern. Different materials always have distinctively different pattern. Infrared spectra. IR spectrum is therefore equivalent to a fingerprint of a substance. Here we have the ultraviolet spectrum of heroin, unique to heroin itself, and the ultraviolet spectrum of amphetamine. Mass spectrometry, I should say, not spectroscopy, spectrometry. A beam of high energy electrons collide with a material, producing positively charged ions. These positive ions almost instantaneously decompose into numerous fragments, which are separated according to their masses. Under carefully controlled conditions, no two substances produce the same fragmentation pattern. As we see here, what we have represented by these different numbers is mass per charge. So 204 mass divided by +1 charge would be 204. 204 divided by a charge of 2 would make a fragment of a mass to charge ratio of 102. So keep in mind that is what's being looked at in these fragmentation patterns. And these fragmentation patterns with the respective mass to charge ratios are often with enough of fingerprints, we are able to identify the material or materials inside a substance, inside evidence. In the top and bottom, the top is for a characteristic MS fingerprint or mass spectrum fingerprint of heroin, whereas cocaine on the bottom is that is the characteristic fingerprint for cocaine. And often there is software that will look at this data and automatically output a likely identification of the molecule, as opposed to the old days where we would have to look at these and look at each individual fragment ourselves. Nonsense. Gas chromatography and mass spectrometry, GC and MS, a direct connection between the GC column and the mass spectrometer allows each component separated through GC to flow into the mass spectrometer as it emerges from the GC column. The separation of a mixture's components is first accomplished by the GC, then fragmentation patterns of each component by high energy electrons in the mass spectrometer will produce a distinct pattern, somewhat like a fingerprint, of the substance being examined. And this is a diagram of how GCMS works. Left to right, the sample is separated into its components by the gas chromatograph, and then the components are ionized and identified by characteristic fragmentation patterns of the spectra produced by the mass spectrometer. Oftentimes, a gas chromatograph instrument is much bigger than a mass spectrometer, and as the different components are separated after GC, or while GC is in process, as each component eventually comes off, that component, while the others are still waiting or traveling through the GC, can be analyzed through a mass spectroscopy. In any case, just around the 32.5-minute mark, glad to have you all. Always a pleasure to have you for this latest edition of Forensics, Chapter 12. As always, likes and subscribes are not necessary, but actually kind of fun to see. Maybe one day I'll get some additional support through YouTube, but in reality, this is just a hobby or a way to support my in-person or virtual classes. Anyways, love you all and peace.